In this video, we're going to talk about the logical operators and, or, and not. These are each logical operators that combine statements and create new statements. The first we'll talk about is and. So and is used to combine two or more statements. And so P and Q, if P and Q are both statements, is written P caret Q, or just that symbol. And so, for example, if we let P be the statement 3 is a prime number and Q be the statement 4 is a rational number, then you can think to yourself, is it the case that P and Q is true? As a second example, if we let R be the statement as shown and S be the statement as shown, is R and S true? So just pause briefly and think about each of those and whether those combined statements are true or false. Okay, so 3 is a prime number. Yes, that's true. 3 is prime. 4 is a rational number. Yes, that's true. 4 can be written as 4 over 1, which is a ratio of integers. And so 4 is an element of the rational numbers. Each of those statements is true. So P and Q is true. So if both statements are true, then P and Q is true. How about the second one? So R is the statement square root of 2 is a real number. So remember, this is the real numbers. These are all real numbers on the real number line. This one is the set containing the empty set has cardinality 0. So this second statement is false, right? Because this is the set containing the empty set. The cardinality of the set containing the empty set, well, that's a set with exactly one element, the empty set, and that has cardinality 1, as compared with just the empty set itself has cardinality 0. The empty set contains no elements. The set containing the empty set contains one element. So that's a false statement. Square root of 2 is a real number. Yes, that is a true statement. So this is a true statement. That's a false statement. Therefore, R and S. Is it true that square root of 2 is a real number and the cardinality of the set containing the empty set is 0? Are those together a true statement? No, that is false because one piece is false. So let's think about writing a truth table for and. So we'll see these more in the rest of the chapter, these truth tables. And basically, we are making all possible combinations of whatever variables are involved in some combined statement. So here we're thinking about P and Q. So we're saying, for example, as we saw above, when P is true and Q is true, then the statement P and Q is true. So I'd like you to just continue filling out this truth table with either writing false if P and Q is false or true if P and Q is true. So pause again, just think about what goes in each of these slots in this truth table. So as we saw above, P and Q is true if both pieces of P and Q are true. If P is true and Q is false, then it is not true that both P and Q are true. So this is false. If P is false and Q is true, then same deal. It's not the case that both P and Q are true, so this is false. If P is false and Q is false, then it is not the case that P and Q is true. P and Q is false. Both pieces are false, so this is false. So P and Q true if and only if if both P and Q are separately true. Okay, so here is another logical operator, the OR operator. So it's denoted with the upside down symbol from what and was denoted. So P or Q. If P is true or Q is true or both are true, those are all situations where this is the case. So P or Q is true if P is true or Q is true, or both P and Q are true. So this is called inclusive or, which is a little, English is less precise. So in English, we have both inclusive or and exclusive or. So an example of, a question phrased with inclusive or would be, do you like chess or bowling? And if you said yes, that could mean that you like chess, or you like bowling, or you like both, right? You could say yes if any of those three things was true. Whereas, if your friend said, hey, do you want to leave at 2 p.m. or at 3 p.m.? And you said yes, that would be annoying, right? Because they're asking an exclusive or question. You want to leave at 2 or you want to leave at 3, but like both is not like a helpful answer for your friend. And so in this case, this exclusive or does not include both. Does not include both. So in English, the word or is not very precise, but in mathematics, we're basically always talking about inclusive or. So if you're in some kind of math-related class and they use the term or, they mean inclusive or. So in math, we always mean inclusive or, unless we state otherwise, unless we specifically say we're talking about exclusive or. So this symbol is their symbol for or in mathematics. And if we're talking about exclusive or, there's different symbols for that. One is like a plus sign with a circle around it, would be exclusive or, but we won't use that too much in this course. So unless stated otherwise, we mean like, do you like chess or bowling situation? You could say yes for chess, yes for bowling, or yes for both. So here are a couple examples again. Let's use the same ones from above. P is 3 as a prime number. Q is 4 as a rational number. Is P or Q true? Then we've got our R and our S. Is R or S true? So think about those just for a moment. So as we noted above, 3 is a prime number. Yes, that is a true statement. 4 is a rational number. Yes, 4 can be denoted as an integer divided by an integer. So is P or Q true? Yes, both are true. So the entire statement P or Q is true. Square root of 2 is an element of the real numbers. Yes, square root of 2 is on the real number line. The cardinality of the set containing the empty set is 0. No, it's the cardinality of that set is 1. Is R or S true? R is true. S is false. Is one or the other or both of those statements true? Yes, R or S is true. Okay, so now I'd like you to write a truth table for or. So again, just take a quick pause and think about what goes in these parts of the truth table, given what P, the truth value of P, the truth value of Q, what are the truth values of P or Q? So take a second to think about that. All right. If P is true and Q is true, then is it the case that P or Q is true? Yes, again, we're talking about inclusive or. So if P is true or Q is true or both are true, then we say that P or Q is true. Here, P is true, so yes, immediately true. Q is true, P or Q is true, yes. P is false and Q is false, no, P or Q is not true. Now let's look at the logical operator not. So given any statement P, one can form the new statement not P or the negation of P. And this is denoted tilde P, so not P. Not P is essentially the same as the complement of P. So it should always include all scenarios where the statement P is false. So for example, if P is that the number 3 is prime, well, that is a true statement. We know that the number 3 is in fact prime. Then not P would be that the number 3 is not prime is one way that you could phrase that, or it is not true that the number 3 is prime, and in that case that would be a false statement. I'd like you just to think about the truth table for not. Actually, it's very quick, right? So maybe we'll just do it together. So this now only has 2 lines in our truth table because we only have one variable that we're talking about. So P is either true or false. If P is true, then the negation of P, not P, is false. If P is false, then the negation of P, not P, is true. So one thing to note at this point is that and, or, and not are logical operators for statements, and they all have parallels in our operators for sets. So and or for statements is in parallel with intersection and union for sets, and similarly not for statements is in parallel with complement for sets. So if we think about, some of the things we've seen with sets, so for example, A and A complement, that's something about sets, and we know that the intersection of A and A complement, what are the set of all things that are both in A and not in A? That would be the empty set, right? Similarly, if we looked at, like, for a statement, P and not P, could that ever be true? No, this is always false. So this is always false. Could it ever be the case that both P and its negation is true? No, this is always a false statement, which kind of lines up with A and A complement being equal to the empty set. Similarly, if we looked at, for any set A union A complement, that's the set of all elements that are either in A or not in A. Well, for any set, any element is either in that set or not in that set. So this would be like the universal set, whatever that universal set is. So universal set. And what if we look at P or not P? So either P is true or P is false. It is always the case, given any statement, that either the original statement or the negation is true, right? Either it is snowing outside right now, outside my window, or it is not. And if I say it's snowing outside or it is not, yeah, that's going to be a true statement. This is always true. And we'll see other parallels between operators for sets and logical operators for statements as we continue. One just last note is that if you've gotten used to the symbols for intersection and union, note that they're sort of pointing in the same direction as their counterparts for sets. So intersection and are pointing in the same direction, and they sort of conceptually are similar ideas, and union and or are also pointing in the same direction and are conceptually the same ideas. So as a last piece here in this video, I'd like you to write the following statements using these new symbols and, or, and not, whichever ones happen to be appropriate for these particular situations. And I want you to think about, not just the words that are given, but like what these statements mean logically. So for the first one, y is equal to 0, but x is not. Can you use any of those logical operators above to sort of rewrite that statement? B, at least one of the numbers x and y is odd. Again, can you use any of those logical operators above to rewrite that statement? So pause and think about that. Just write it down on a piece of paper real quick. Okay, y is equal to 0. So we could keep writing it out like this. We could also just write y equals 0, but x is not equal to 0. So one way we could write that is x is not equal to 0. We could write that with a not equal, like with a line through it, but because we want practice with the not operator, let's use it is not the case that x equals 0. Now, how can I connect these two statements? Y equals 0, but x is not equal to 0, but it is not the case that x equals 0. That is really an and, right? So this but is really an and right here. Y is equal to 0 and x is not equal to 0. So this is the operator that would go between those two statements. So this right here is logically equivalent to that statement below. Y is equal to 0, but it is not the case that x is equal to 0. Next one, at least one of the numbers x and y is odd. This one's tricky because there's an and in it, so you'd think that we might use the and operator, but think about logically what this is saying. At least one of the numbers x and y is odd. So when would that be true? That would be true if x is odd, or y is odd, or both are odd, right? Because at least one means x is, or y is, or both of them are. And therefore, this is an or operator, not an and operator, even though we see and in the words. So this is x is odd, or y is odd, would be our way of writing this using some of those operators above.